everyone. Our first talk today will be by Yves on non-abelian Rees construction and motives.
Thank you very much. Already this week we heard about this function, the classical one, that you need else to Hodge filtration in the non-abelian. Here there is non-abelian in the title, but it is not the same sense. This construction is the most basic case. So that K will be a field of characteristics throughout my talk. And the Rees construction has to do with comparing the filter vector space with graded vector space. And so the category of filter vector space and by vector space with those given separated expression, X by Z. Morphisms are just linear maps which are compatible without the filtration. And then this is there is a natural tensor product here, and this is filter vector space is non-abelian. This is a rigid tensor category. And when one passes to the graded underlying space, one gets a tensor functor from the filter vector space to the graded vector space. Then the Rees construction, which is due to Rees, very old construction, it appeared first in commutative algebra in the special case of I-itic filtration, and was largely generated by Gersten Haber. Is the following construction. One starts with a filter vector space, and one introduces certain indeterminate X and the Kx submodule X 1 over X tensor B, which is defined in this square. So X minus I, K of X, and then the set I here. And this construction can be interpreted geometrically as providing a GM equivariant vector bundle on the affine line. So X is the coordinate of the affine line. So this is very classical. And this construction gives rise to a commutative diagram of tensor factors, which is one. So the vertical just taking the graded piece. Here, the horizontal is equivalence of category. It's a vector space, GM equivariant vector space over the affine line. And if I consider the fiber at 0, I get just the representation of GM. And again, at the bottom, this is the equivalence of category. This is an interpretation of this functor as just taking the fiber point fixed by GM of GM equivalent vector. If instead one takes a fiber at 1 instead of 0, then this functor is still fully faithful, and this gives an embedding, full embedding, an embedding of filter vector space in the abelian category of vector space. So, of course, so the affine line here appears clearly as a deformation space between the category filter vector space and graded vector space. And the graded vector space, in fact, is just a category, a quotient category of filter vector space by its maximal tensor ideal. So ideal in this talk is just a set of morphism, which is stable by vector space, it's stable by composition and by tensor product. Of course, this construction can be generalized. Instead of just taking bare vector space, one can take other more complicated filter objects, and this was the case in Daniel's talk, lambda connections.
So here's the maximal tensor ideal under morphisms degree -1.
I'm sorry?
So here's the maximal tensor ideal as morphisms of degree -1.
Taking the question as the ideal, but you don't change the object, but you
Sorry, I mean, in this particular example, to
this one?
describe the maximal tensor ideal.
yes, here this is a quotient by the maximal tensor ideal. Yes, yes, exactly. Yes, here too. Okay, now I'm looking for non-abelian analog of the Rees construction. Maybe I should have said before that instead of GM, you can take the power of GM and you get many filtrations. So it's the same story. But if you replace GM by an arbitrary reductive group, maybe non-abelian, this is the topic of this talk. And this is non-abelian in this sense, not non-abelian of theory in this case. So there are two obvious questions in that case, but we'll replace the deformation space in one. This should be G space. And the second question is a little bit goes in the opposite direction, how to describe concretely tensor categories of equivariant vector bundles, like G of X, for more general spaces X. So X is just A1 and G is GM. The concrete description I have in mind is just a description in terms of filtrations. So I start with the second question, so which is how to describe the category of equivariant vector bundle and reductive group G, which acts on a certain affine right X, and a general, some rather general answer. First, for in the case of toric varieties, the answer was given by Kliashko, Lampeco, and more recently by Ashok in the case of the spherical varieties. So let me recall what this vocabulary is. So G is G is a reductive group, okay, without my talk. So the basic notion, this talk is the notion of quasi-homogeneous G variety. In the literature, it's also called prehomogeneous G variety. This is exactly the same thing. This is a G variety which admits a dense orbit, which will always be denoted by X naught, which is a homogeneous space under G. So you can think of a quasi-homogeneous G variety as a partial compactification, G equivariantly, of a homogeneous space. For instance, A1 with the GM action. So now a spherical G variety, usually they are studied and defined when K is algebraically closed. So this is a special kind of quasi-homogeneous, usually normal, G variety, which remains quasi-homogeneous if one restricts the action of G to some Borel subgroup B. So this is the geometric description, but it has a more useful for application equivalent formulation in representation theoretic terms. This is equivalent to say that for any representation, finite dimension representation of G, the H invariant. Okay. The H is I should have written that the homogeneous space is G over H. Sorry, there's something missing here. The H invariant has dimension at most one.
Can you repeat H?
It will occur in the next slide. I'm sorry for that. There was an X0 in the definition of quasi-homogeneous. This is a partial compactification of a homogeneous space X0, and X0 is G over H, because K is algebraically closed, so that's the point.
Thank you.
So this is any isotropic proof.
It's a stabilizer of the point.
Yes, exactly.
The value is irreducible.
So,
The value is irreducible.
oh, yes, yes. Sorry, yes. For any irreducible, thank you. Yeah, of course. Any irreducible vector and H from space of at most one. So a very important notion in this talk will be the notion of fixed pointed G variety. This is a G variety which admits a unique closed G orbit, and which, moreover, is just a point. This can be, if the variety is affine, this has a very simple translation. If it is defined by a affine algebra A, so G acts on A, and I ask that the G invariants A are just reduced to the field K. So that's for the terminology. Now, about spherical varieties, they are very well studied because there is this combinatorial theory by Briand, Nula, and Gauche, which gives a purely combinatorial description of those varieties in terms of certain one-parameter subgroups, some other data called colors, but it is very similar to, so it's generalization to the combinatorial description of toric varieties. It's just a little bit more complicated, but it's exactly in the same spirit. So now here is the solution to question 2 that Ashok proposed. It's a case of spherical varieties. For any fixed pointed affine spherical variety, the category of G equivariant vector bundle on X can be described, or is tensor equivalent, to a certain category, a tensor category, whose objects are just a representation of G, and whose morphism are H linear maps, which preserve certain specific filtration attached to the mu J. This is very explicit. I won't enter the detail, but this is quite explicit. So this is really a direct generalization of the classical Rees construction interpreted going from equivariant vector bundle to the world of filtration, multi-filtration.
So why is the fixed point hypothesis important here? It's not possible to give such a description in general.
It's possible to give a discussion in general, but the statement is not so clean. And also one reduces always to this case by some theorem by Luna, slice theorem. So let me tackle the first question, which was, what is the deformation space in the non-abelian Rees construction? So when GM is replaced by an arbitrary reductive group. And here there is a completely general answer by Peter O'Sullivan I'm about to describe. So one starts with a tensor category, which has nice property. So it's called C here, and it is a tensor category which is K-linear, symmetric, which it means that every object has a dual, and it's moreover even. Even is not so standard terminology, but it means that any object is scaled by some exterior power.
Do we assume characteristic 0?
Yes, from the beginning. K is always a field of characteristic 0, yes. And moreover, I require that the morphism of the unit object is just K. So in this is a general result. that so this is such a category as a maximal tensor ideal, and that's the quotient C by the maximal tensor ideal. So the quotient has the same object, but just the morphism. The same is always a semi-simple Tannakian category. And this theorem, due to O'Sullivan, one approach is due to O'Sullivan, is that the projection from C to C bar, so mod out by the tensor radical, admits the tensor section. So I won't present a proof or sketch of proof, but I'm happy to answer some questions later about this. This is very important in this talk. So if C is even with the projection of C to C modulo the maximal tensor ideal as a tensor section, which I denote by sigma. So now let me go back to the question, admitting this is very important facts. From the fact that C bar is semi-simple, it's very easy to see that such a section has a right inverse, which I denote by theta. And if I apply theta to the unit object, it's quite a formal thing in monoidal categories, that this is an algebra. And I denote it K algebra, I denote it by O of X. X is the spec of this algebra. And this is an algebra in the in category of C bar. In particular, if C bar is a neutral Tannakian category, that is, if it is equivalent to representation of G, of K, then this X is a fixed pointed affine G variety. And moreover, this is a theorem that the category C you have started from is always equivalent to a category of vector, equivariant vector bundle over X. So such category have always this form. This can be rewritten in which way C is equivalent to the category of vector bundles on the quotient stack X divided by G. So this fits very well this program of geometrization of categories, which was initiated by Simpson, I think, introducing the Durham stack and vector bundle of the Durham stack to describe the connection. And so many years, this is very trendy now, but this is a very general answer for even rigid symmetric categories. Not here that C is not supposed to be abelian.
Where is even important here in the construction?
It's if it is not even, you don't have a section.
Okay.
This is very important, and also you don't have a Tannakian category. Okay.
Would you assume that idempotent give direct factors?
Oh, sorry. Yes, there is something missing. Yes, it's pseudo-abelian. Thank you very much. Yes, I forgot to write it. There is one more assumption that it should be pseudo-abelian, because such kind of categories are always pseudo-abelian. Okay, so let's do an example. Of course, the classical Rees construction is an example, but this is another one. Let's take for C the category of vector bundles on the projective line. Famous theorem like Grothendieck, all objects are sums of rank 1 object, or n, and it's an integer. In this case, the quotient by the tensor radical is just a category of graded vector space. So G is Gm. And the deformation space now between C and bar is the affine plane, no longer the affine line. And one finds that C, with vector bundles over projective line, is equivalent, tensor equivalent to the category of GM equivariant vector bundle on the affine plane. And taking the fiber at the generic point P1, embed C into the category of vector bundle or vector space over K of X. But here there is no embedding of this category into K-linear abelian category. So this is not quite like the original Rees construction. And also the deformation space is no longer quasi-homogeneous, equivariant. So in the third part of this discussion about non-abelian Rees construction, I will put some extra assumptions. It constrains the variety X, which force it to be a fixed-pointed affine quasi-homogeneous variety, and in fact, which can be computed by a formula. So let give the reductive group or K characteristic 0. Now I consider I start from X, which is a fixed-pointed affine quasi-homogeneous G variety, okay, with open orbit X nodes, which I assume that it has some rational point, and I write X node as the quotient of G by H, stabilizer of this of some point. Then, if one looks at the category of equivariant vector bundle, which I denote by C, this is a pseudo-abelian Wedge tensor category, which is even, and it has the following properties, 3 properties. First, yes, it embeds into the category of vector space just by taking the fiber. X node. The second property is that there exists an object such that any object is a direct summand in a certain some tensor construction. Direct summand is an important word. This is because yes, so I want to deal with so I deal with reductive groups and not pro-reductive groups. So it's the equivalent. And the third category, the third property, which is I shall not be very precise, but says that so the morphism in C between the unit object and some tensor construction is degree, by degree Mn. So the degree in M is V tensor n, and n is V dual tensor n. Is generated, tensor generated by a set of morphism of lower degree, I and j less than certain constant. Finite generation assumption. So any category of like this has these 3 properties. Now we will see that the converse is true. So for any pseudo-abelian rigid tensor category which satisfy the first property to have a fiber functor, the second property that any object is a direct summand in some tensor construction, and the third property which says that so the morphism are generated in low degree, then the other Sullivan construction provides X provided by the O'Sullivan is a quasi-homogeneous variety, it's fixed-pointed, affine, and it has a irrational point in its valid X node. And moreover, this gives rise to a commutative diagram of tensor pointer, exactly as in the Rees classical Rees expression. So this one here, this is a quotient by the maximal tensor ideal. This category is always equivalent to a category of vector bundle G over sum X. So this X is the one provided by the Austin-Van construction. And on the right-hand side, the vertical functor is just taking the fiber at the fixed point.
What is the property which forces the existence of a rational point?
This is property P1.
P1 was.
That's, P1 is that it embeds into, there is a fiber functor.
Thank you very much.
Not in a vector K dash for some extension, really in a vector. Okay, and moreover, this can be elaborated, and this provides an anti-equivalence between such a category C with a property P1, P2, P3, plus one has to fix a fiber functor between this very simple C bar, the quotient by the maximal tensor ideal, with the category representation of G. Then if one, so these two data is anti-equivalent to the category of fixed pointed affine quasi-homogeneous variety, which can be defined in the big orbit. So an example.
I am confused. What is a two category and a third category? So
Yes, in fact, you can. Yeah, I can say a word. The category of fixed pointed affine quasi-homogeneous varieties is just one category. I can see it as two categories, and that in that respect, this is an anti-equivalence of two categories. So the example is I take just a representation of the additive group. Here's the group G, which controls the C bar is category of representation of G. This is SL2. This is just a version of formulation of the Jacobson-Morozov theorem. And the deformation space between C and C bar is again the affine plane. The X node is just the affine plane minus the origin, and it can be written as G shunted by H, where H is again the Z2. The category of GA is equivalent to the category of SL2 equivariant vector bundle on the affine plane. Okay, now I give a formula to this. Seems very abstract, but this is very concrete. If K is very close, or more generally, if all irreducible representations of G are absolutely irreducible, then so I fix a faithful tensor functor. Okay, then the formula is the following for the algebra of X. So this is a sum over all indecomposable objects in C, which is the same as irreducible representation of G, of the morphism between this object to the unit object, to the section of the dual tensor, so the edge of this object in so the infinite sum in general, so this is in representation G, where G acts only here, right? Okay. And in fact, this is so this is nice because there is a nice, you see on this formula that if you, of course, you have this omega. Here, these are just morphism in the category C. You can take omega, so this embeds into this some vector space. So in particular, this embeds into omega of the dual V, so that O of X is in fact a subspace, but it turns out to be a subalgebra of this thing, because this thing is exactly OG by the famous formula, where G acts only on the second factor. So this is a very concrete formula, very useful when one want to use this theory, one always use this one. Okay, now some comments. If one drops the third condition, which was a bit cumbersome, which says finite tensor generations, that all morphisms are generated tensor space by some tensors of a low degree, then X is no longer finite dimensional, but it is always a countable limit power of fixed point quasi-homogeneous varieties, not by Xn, but they have all the same group G and all the same orbit Xn naught. It's just the boundary which changes.
So it's projective limit.
Yes, yes. Yes, sorry. I can give you a funny example, which I call the Fibonacci category. If you have a tensor category generated by two objects of rank 1, and you assume that the morphism between L1 and L2, L1 tensor A to L2 tensor B, only if A divided by B is less than 1 plus square root of minus of 5 over 2. Then the X is a limit of a tower of a toric surface, which correspond to there are some cones. The cones are just the angles are just a Fibonacci number. So this condition P3 is really necessary to have a finite dimensions. So, but there is there's a nice factoriality, as I already mentioned, and one can translate, one can, yes, state the properties of the functors between two such categories and properties of the J-equivariant morphism between the corresponding quasi-homogeneous varieties. For instance, the functor is faithful if the image of this morphism in the opposite direction meets the open orbit. Faithful, fully faithful has also a traduction. This X is just a quotient. And full essentially surjective means essentially that this X is just a close G subvariate. Okay. So now let's apply these to motives. So I will deal with Grothendieck motifs or some homological equivalence, so pure motif, defined in terms of projective smooth variety over a field small k, capital K is a coefficient. And the morphisms are given by algebraic correspondence, 0 modulo homological equivalence. Okay. Take them with coefficient in our field K, capital K. So this property P2 that any object is a direct summand of some tensor construction will be available if one considers motif cut on product of finitely many varieties.
The field K is characteristic 0.
Yes. No, the small K, no. Later it will be a characteristic.
And so,
but capital K is a characteristic. So there are
so
some.
you fix one common theory.
Yes. So, but so P2 is okay. One just has to consider only finitely valued motif, the basic motif. But P2 there is already a problem because we need even category. So to have even category means that any object is killed by some exterior power. One needs to twist the commutativity constraint, and so assume that the QNet projector on the even part of the cohomology are algebraic. Let's assume this for the moment, and we'll return to this point later. Then, if one assumes this, our category C, then one can apply the non-abelian Rees construction and one get G and X, such that C is also commutative, which satisfies the so-called sign conjecture, can always be viewed as a category of G equivariant vector bundle on some X. This is O'Sullivan construction. So my aim is to try to convince you that it is a useful viewpoint. So here the C bar, so the quotient by the maximal tensor ideal, is just the corresponding category for numerical equivalence. This G is just a numerical motivic Galois group that I can category attached to this bar. Behind this, there is this Janssen theorem, semi-simple. And now we're applying this previous theorem, so we get an X, which is the limit of a tower of fixed-pointed affine quasi-homogeneous varieties with the same G and the same open orbit G over H. So what is H? So I describe what is G here. This is numerical motivic Galois. Well, I assume for simplicity that the QNet projectors are algebraic and the characteristic of the base field is 0. In that case, this H is just a motivated motivic Galois group, which I need to produce long ago. And so to speak, this X is a partial compactification of the quotient of the numerical motivic Galois group by this motivated motivic Galois group. This motivated motivic Galois group, the Tanakan group, the category which one obtains from C by adding formally the inverse of the Lefschetz operator attached to polarizations. So now we have this famous Grothendieck standard conjecture. The homological equivalence is the same as numerical equivalence, because it's finer a priori. And for C, for our category motif cut on by I, this category is just equivalent. This conjecture is just equivalent to say that X is a point.
So X was, can you?
X is our deformation space. This is given by the Rive O'Sullivan construction. This quasi-homogeneous.
Compared to XN, the limit of CXN, it was what?
The limit.
It's just a limit, so that would mean that all CXN are 1 point. Or do I make
Yes,
this?
yes, yes. But it makes no harm to put this condition because this category C is a co-limit of category which has P3, so one can reduce immediately to find that. So it's, the idea is that yes, moreover, by this construction, the G orbit in X correspond to equivalence if unhappily the standard conjecture is not true, there may be several adequate relations between homological equivalence and numerical equivalence. We are not even totally ordered, but they correspond exactly to G orbit in X. This gives a kind of geometric pictures. So in the conclusion, in the motivic complex, this conjecture, the deformation space, X, appears as an obstruction to the standard conjecture.
Under the assumption that the QNet components are algebraic.
Yes, which I shall comment later, but yes.
Is there an obvious a priori bound on the dimension of X, depending on the family Xn you started with?
Well, it's the dimension of G gives.
Yeah, but assuming, I mean,
no, there is.
assuming you can't.
In general, no, nothing better. So, but as you see, I just follow the standard strategy. There is a problem conjecture. So I just build an obstruction, a mathematical object, which is an obstruction, and I try to study it and to see that in some special case, this obstruction is triggered. So this is what I will do in some example. So an illustration. So I use the fact that this X, as explained as in the formula, it's amenable to computation. Let me look at the case of the compact pencils of abelian varieties. They are useful because they are related, and K is small K is a characteristic source. They occur in a
Pencil means S of dimension 1.
yes, and compact also.
Compact means S. This is
Yes, everything.
It's an abelian scheme.
It's an abelian scheme of a projective smooth curve. And so this is a way. So it's used in the proof of Gardens that absolute Hodge and can do something. It more, they are motivated. It's like a complex variety, and the construction which is behind is to look at those compact pencils. So, but here one encounters again this question of the Punnett projector. I don't know whether the Punnett why it's always, but I say that I don't care because you can always replace S by a finite type covering system, especially by two covering, and then you can use the involution and look how it acts on it separates the two. This is a trick, but it works. So one should not stick at the sign conjecture on A. We can replace Y1. So this is the way you can bypass.
Because there is no abelian scheme on P1, this is what you said. We always
No, I mean, let's assume that S0, you can replace this by the fixed part.
No, but you need to cover S.
Yes, I eliminate, yes.
Yeah.
Yes. I will assume that S is homogeneous at least once.
Thank you very much.
Yes. Okay. So in any case, one can apply, then one can run the risk construction, this machine, and one can try to compute what is the X, what is the deformation space. Then this is quite explicit. One can do this, for instance, in the setting of family Bell cycle, this thing. And one finds that generally one can compute things, but one always finds there are two possibilities. Either it is a prime, fortunately, then the photonic standard conjecture D is correct in that case, or there is another possibility, but which is quite explicit. And in that case, it's the limit of three-dimensional explicit affine toric varieties and complete the codes. Of course, for abelian force, recently Markman proves that it is a point. So now let me turn to this question whether case when one can prove that the obstruction is trivial. So new case where photonic standard conjecture D holds. We will use the fact that take advantage of the fact that this the theory of quasi-homogeneous varieties is especially in the affine case is very well developed, in fact. And there are some criteria that it says there's a criteria by Luna, which I will mention, that for some condition on G and on H, the quotient G over H does not admit any partial compactification. So this X is G over H, but since it has a fixed point, it is a fixed, it is a point. This will be the argument for the first criterion. So I give two criteria. and to application. So the setting is exactly the same as before. So I have an even pseudo-abelian or K, such that all objects are direct summand of some tensor construction in one specific object. And I give myself a faithful tensor functor to the vector space over K. K is so the ring of endomorphism of the unit object, C. And the Jx are as before the quasi-homogeneous variety attached to H by the O'Sullivan construction. I denote by X naught the H open orbit, and C bar is the quotient of C by maximal tensor ideal. Same notation as before. So the first criterion assumes that the K is algebraically closed with characteristic 0. And there are two assumptions that as an object of C bar, the quotient category, this basic object B is isotypic. So if you think of C bar as a categorical representation of G, it means this corresponds to isotopic representation of G. And the second condition is that there is a certain reductive subgroup of H, which contains the homotopy of omega of this object, of the realization of this object, such that the endomorphism commuting with H dash is the same as the endomorphism commuting with G. Not for all objects of C, but just for this object, particular object. So this is the same as the endomorphism of this object in the category C bar. The conclusion is that C is subsimple, X is a point. So let me sketch the proof. This is not long. So first one, I replace this object by decomposable factor. This change nothing. I assume this object is decomposable. It corresponds to irreducible representation of G. Then, since K is K bar by sure, the centralizer in G or even in the automorphism of omega of G of this group H dash is just K star. Thus, we have a quasi-homogeneous G variety with open orbit G over H, such that H contains a reductive subgroup with the properties that the centralizer in G of this reductive subgroup H dash is contained in H dash. And here, this is the theorem of Lunar, that this implies that X is G over H. This is a strong theorem. It was published exactly 50 years ago in Inventiones. It relies on the stress vector, but it's much powerful, much more difficult. But now,
What do we have the condition centralizer of H lies in H1? Centralizer.
Because K star is by assumption in H. This condition.
You said, I didn't hear what you said about Luna's theorem depends on what? It uses what, the Luna's theorem?
The slash theta.
Okay.
But so the conclusion of Luna's theorem is that X is a homogeneous space, but X has a fixed point, so it is a point. To application to abelian variety, we take an abelian variety over a field K, such that the endomorphism, the center of the ring of endomorphism of A is Z. I don't assume that K is algebraically closed also. Then the numerical equivalence is L-adic homological equivalence. for algebraic correspondence on powers of A. So in characteristic 0, this is well known for many, many years, but Lieberman. So I assume that K is of characteristic P, different from L, and I also assume that it is finitely generated. Assume this. And I shall extend capital K to Q and bar. In fact, this story to know whether numerical equivalence is homological equivalence is insensitive to such extension, because it's the question of certain pairing is degenerates, you can extend scalars, etc. Okay, then now the assumption of the proposition are satisfied, taking for H dash the Zariski closure of the image of Galois. And why is it satisfied? Because you have T Zarin, which gives exactly this condition. If you take for this object the H1 of A. The endomorphism of Galois of the H1 étal with coefficient in Q and bar is the same as the endomorphism of A tensor Q and bar. Okay, so now I down to my second criterion. I give myself now K is no longer algebraically closed, and I assume that there is a quadratic extension. So, and I denote by iota the involution. So we have our group G, and I perform the extension of scalar to K dash. The assumption is that this group is abelian diagonalizable. And moreover, that the iota acts as -1 on its character group. Conclusion is that C is. So let me sketch the proof. So I denote by omega dash.
This condition is that
I'm sorry.
GK prime is isogenous to a product of element of norm 1 in K prime.
Yeah, exactly. In the case, I have the real as the complex, it just means that it is compact. So let's extend also the fiber factor to this quadratic extension. Then one has a formula when one applies, so this C dash has the same property as C, so one can perform the Rees oscillator construction. Let's give ourselves a quasi-homogeneous variety X dash under G dash, under G, denoted by G dash in GK dash. And I have my formula, which here simplifies because here this was the sum of all indecomposable objects or irreducible representation of G dash, but they are all characters. This is diagonalizable, so I index the sum by the character of G dash, and the formula was C dash 1, so V1, but it's the same as 1 and the dual, so V inverse of the character, and omega dash V. So V chi is a one-dimensional K space, K prime space attached to the character chi. So G acts here via chi. And this is algebra of the algebra of G dash, which can be written in this way. So this formula. So now I denote by this chi, so capital Chi, the set of chi here, characters, such that this piece is non-zero. And this is a monoid, just because this C dash, this omega dash is restful. So if I have two isomorphism, I take the tensor product and omega dash. This is also non-zero. So this is a monoid. we would like to prove that it is a group. So we have to prove that if chi is in this set, its inverse is 1. So but then we use the complex conjugation. I mean this solution. It acts functorially C dash because everything comes from K, in fact. And so we have this formula that the action of the natural action C dash on this space is the space, the one-dimensional space attached to the action of iota on the character. This proves that this set is invariant by iota. But now I have this assumption that the iota acts by -1. So it means that the set is minus this set. And this proves that this set is a subgroup of the group of character of C dash. And this proves that there is a subgroup, diagonally subgroup, such that X dash is G dash, but H dash. But X dash is fixed point and is a point, and so is X. And so C is C dash, C bar. So the question is a new proof of theorem of Clausen-Pierre-Levy. So we consider an abelian variety of finite or the closure of algebraic closure of finite field of P, and denoted by AI the simple factors up to isogeny, and F over Q will be a CM Galois extension containing the centers of the endomorphism of the factors. So this is a CM Galois, and I consider C, I denote by C the complex conjugation. This is F, this is the mistake. So the theorem, which is Clausen with an improvement at the mean, that consider n-adic cohomology for L different from P, L which satisfy moreover this condition that there is a place of F, this field F, above L, for which there is an evolution of the completion at lambda this will be my K dash, such that for every embedding of each of this F into this K dash, there is this commutation law that if you consider this complex conjugation F, there is no dash, and composed with tau, this is the same as tau composed with iota. The conclusion is that numerical equivalence is n-adic logical equivalence for algebraic correspondence on powers of K. So I will deduce this by a direct application of the last criterion. So let's define a K dash, which was the completion of this at lambda of F. I consider the fixed field denoted by K, but K contains a QL, of course, because everything is QL is continuous n-adically. And so in particular, I have the n-adic realization comes from K, even comes from QL. And so I consider for C, not exactly as before a category of pure motif, but the ungraded version, so which means that I consider correspondence of any degree. So I identify the Tate unit. So this has the properties that I don't see any longer the Tate twist, which has the group GM, and on GM the complex conjugation, the character acts by +1 and not -1. So I don't want this. So I kill this, and but this is the same to prove the numerical equivalence is homological equivalence in these ungraded settings. Now let me, let S be the torus defined by as a product of tori, the kernel of the norms, by over the fixed field by C. Then it turns out that G is contained in either this, so the extension of S to K, or maybe the product of extension of S to K by Z over 2Z, if one of the AI is a supersingular elliptic curve. In that case, then I can group, consider ungraded correspondence is just Z over 2Z. Okay, but this is so the extension to K dash is diagonalized. Iota acts by -1 on here. So one can apply the criterion and one gets the conclusion. Note that this new proof, unlike the previous proof, does not really use the special structure of the commutative abelian variety. So it extends to CM motif, ungraded CM motif, maybe a priori not related to abelian varieties, but provided one can prove that the G has this property, that it is compact. Oh, I didn't say why this group is contained in isomorphism. This is because this fact occurs at least twice in this conference. Abelian varieties over finite field are all CN. Well, I think I'm finished. So.
Questions?
So can you say a bit about is there anything you can do if you don't know the sign conjecture?
I'm sorry?
So can you say a bit about like if you don't know the sign conjecture, is that right?
Yes, first of all, in my application, yes, at least here, so by that key, so it's not. Otherwise, the only things that I can say two things. Sometimes by the trick, I explain that in the case of compact pensive abelian variety, one can bypass the conjecture. And if you cannot do this, you have to abandon and to replace motifs as defined by Grothendieck using algebraic correspondence by some what I could call sign motif or something like this. Instead of algebraic correspondence, this is the same philosophy as motivated cycle. You consider so here beta algebraic cycles on product. And so here you don't know any longer that this is an algebraic cycle. But you take a product and you project here. So this is a little bit, so get a little bit more morphism than just algebraic correspondence, less than motivated it's in between, and you have a nice formalism of this. So you can sign motif, and so the conclusion of this construction will apply to this sign motif, not to Grothendieck motif. But in any case, this is not conjectural. Just the conclusion is weaker.
Yeah, I had a question. You didn't say anything about variational aspects. So suppose you take variational aspects. You take a family of varieties over some base. Then you make this construction for each fiber. So you get this group. You get this X varying depending on the base. Can you say anything about that? The locus where
Well, this is even more complicated than the problem of variation of the monodical groups.
So-
This, you see, at least for the age, for the in characteristic 0 and so
For the age, you know.
age, you have good properties for the motivated. Even for the G, it's not clear that you don't have. So it's not clear. And for the X, it's even more difficult. I don't know. I don't know the general answer.
Other questions? Okay, let's thank Yves.